Welcome back, stats. We're going to do day 2 of probability and getting into 3.2, what we call conditional probability and the multiplication rule. We're going to go through bell work, reviewing some of 3.1 basics of probability. We're going to go through that homework quiz, obviously the objective and essential question. Then we're going to go through many examples for 3.2 conditional probability. What is it to be conditional, the conditional probability? And then we're obviously going to go through the closure, homework, summary, so forth. I do have another bell work question on top of these three in the next slide, but you don't necessarily need to listen to that one. I just want you guys to pay attention to these three because these three will be on the homework quiz. I'm telling you that they are. Take a minute. Write them down. Let's get started. Identify the sample space of the probability experiment and determine the number of outcomes in the sample space. We randomly choose a multiple of 4 between 20 and 40. What does this look like? Well, first off, it's going to ask you, number one, it's going to ask you what the sample space is. So I'm going to just abbreviate sample space. This sample space, we need to list out the sample space in our fancy braces. Well, if it's a multiple of 4 between 20 and 40, well, 20 is a multiple of 4. And it says inclusive. So that means I'm going to include 20 and 40 if it is indeed a multiple of 4. Well, it is. So I'm going to include 20. Multiple of 4 is, the next one is 24. The next multiple of 4 is 28. Next one is 32, 36, and then 40 inclusive. So that's what it's going to ask you first. The second thing it's going to ask you is how many outcomes, and then determine the outcome. So this was our first step right here, probability experiment, find the sample space. The second step is determine the number of outcomes. Now we just count 1, 2, 3, 4, 5, 6. So we write 6 outcomes. And yes, guys, it is that simple. Boom. Done. Next one, assuming that no questions are left unanswered, in how many different ways can a 9-question true or false quiz be answered? So this one's kind of tricky, but it's really not. So you have how many questions? You have 9. So 1, 2, 3, 4, 5, 6, 7, 8, 9. And then how many different answer choices do you have within those 9 questions? You actually have 2 because it's true or false, 1 and 2. So that means it's going to be 2 times 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 2. Which this means 2 to the 9th power, which reduces down to 512. So that means you have 512 different ways that you can answer this true or false, 9-question true or false quiz. Okay? I hope that makes sense. Let's go on to the third one. Probability experiment consists of rolling an 18 fair-sided die. Whoa, D&D life. Rolling a number that is divisible by 5. How can I do that? Well, first of all, I want to list out my sample space. Always list out your sample space. What is that? My sample space is literally 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, and 18. Okay, so this is your whole sample space right here. Now watch this. We want rolling a number that is divisible by 5. Okay, the only ones that are divisible by 5 are 5 right here, 10, and then 15. Okay, so what does that mean? This is my first step. My second step is then, okay, what's the probability? Okay, find the probability. That's what I want to do. Find the probability. Well, the probability of a number that is divisible by 5 equals 1, 2, 3 different outcomes. 3 different outcomes out of a total of how many? 18, which reduces down to 1/6, which is, of course, roughly 0.1667 repeating. So that is my probability. Again, this is not that difficult of math, guys. It's really just kind of analyzing the problem that you have. So make sure, again, you look at the key that I posted on Google Classroom. You follow along with your notes. because it's definitely helpful. Let's erase, and then let's go to this question. This question is kind of a bonus Bell question. You don't necessarily need to go through it, but it is going to be on the homework quiz, so just letting you know. The access code for a gym locker consists of 3 digits. So I'm going to look at this. So 3 digits right here. 3. I'm going to do my blanks. Each digit can be a number between 1 through 5. So that's 1, 2, 3, 4, 5. So that's 5 different numbers. And each digit can be repeated. So I'm going to have 5 times 5 times 5, which is 5 cubed, which is the same thing as 125. So 125 is a different number of possible access codes, and that's what A wants. Find the number of possible access codes. We already did that. A is 125 ways. 125 different access codes. Okay? Now for B, what is the probability of randomly selecting? Probability of randomly selecting the first access code. Okay, so selecting the first access code. So I'm just going to say probability of first. It doesn't really matter. Well, there's only one correct access code, right? So 1 out of how many total? 125. And then boom, that's my answer. Okay? C is going to be find the probability of not selecting the correct access code. And this is actually really easy. Okay? This is actually very simple. What are all the access codes? So the probability of not selecting the first access code. So not, that's my complement. It's just literally the complement. It's 1 minus 125, which in this case would be 124 all over 125. So really it's all the other codes that isn't the actual access code. And there's 124 access codes that don't work the first time, whereas there's one access code that does. So this is a complement, and this is the first access code that does work. Okay? Very simple. I don't know if Math Excel will ask you for decimals, but you just plug them in decimals, plug them in your calculator, and then you get the decimal. Sweet. Let's erase. Let's move on. Go ahead and start on the homework quiz. It's going to be 5 questions, 20 minutes. Of course, you can use your open notes. Begin your notes for today. It's 3.2 conditional probability and multiplication rule. Again, that's on Google Classroom. Go ahead, print off the notes, the Google Doc if you need to. Make a copy if you want to do the online stuff, or just print off the key and just do the notes by hand. But follow along, please. I'm going to brush through this, but take the homework quiz. I want to mention this since this is your first homework quiz. Please review your answers, because if you don't review your answers, then you may have gotten the right answer, but you maybe didn't simplify, or you accidentally did like a fat finger and you accidentally put a different number, or you didn't divide correctly or something. You can send me that partial credit request. You can send me like, hey, on the subject line, just say homework quiz 3.1 basics of probability. Say, hey, Mr. Carlson, I accidentally did this. Is that worth partial credit? I can say yes or no, okay? But most of the time I do give you the partial credits, okay? So please review your answers, and if there's any partial credit that you would want, then send it my way, okay? If you need to pause the video, go pause the video, and so that you can start on that. But if you're good, if you're solid, let's begin the notes here. Again, make sure you print off the notes. If you don't have access to a printer, write them down. You need to take notes, okay? You can use the notes on the quiz. I don't know why you would not use the notes on the quiz, because you freaking should, okay? So, write down the essential question. How do I calculate the probability of conditional events? What is the difference between independent and dependent events? Okay, let's get to it. Okay, what's the definition of conditional probability? Conditional probability is a probability of an event occurring given that another event has already occurred. Okay, I'll say that again. Conditional probability is the probability of an event occurring given that another event has already occurred. So the conditional probability of event B occurring given that event A has occurred is denoted by this fancy thing. It's called the probability of B given A. So that little line there is like such that or given. So the probability of B such that A, or the probability of B given A is read the probability of B given A. This is the one formula that I would probably have you guys write down, just kind of squeeze in your notes there. The probability of B given A is also an intuitive formula. You can use this, the number of possibilities for event B and the number of possibilities for event A. I don't really like this formula, but it is intuitive. The formula that I personally like using, and I'll be using a lot, is this: the probability of two events A and B with probability of A not equaling 0. Whoops. Is this. This is the probability of A and B all over the probability of A. Okay? This is the probability of A and B all over the probability of A. Now, the reason why I like this is because it's less intuitive than this, and this intuition formula right here works, but it doesn't always work. This formula always works, okay? And we're going to be using what we call two-way frequency charts. We're going to be reviewing a lot of two-way frequency charts next week, but we're going to be introducing two-way frequency charts right now, and this formula is awesome with it. So make sure you write down both these formulas. This is the intuitive formula, and this is more of like an actual formula. I'm going to explain both of them as we go. All right. Man, it's annoying. Two cards are selected in a sequence from standard deck of 52 cards, 52 playing cards. Find the probability that the second card is a queen, given that the first card is a king. Now, you're going to assume that the king is not replaced. What does this mean? It's going to look like this. So the probability of a queen given that the first card is a king. What does this mean? Okay, so because the first card is a king and not replaced, the remaining card then, after you select, so after the first card is a king, and then the next card, the remaining deck will now have a total of not 52 cards, but 51 cards. Because again, you're saying find the probability of the second card is a queen, given that your first card is a king. But your king is not replaced. So you have a standard deck of 52 cards. You pulled up a card, it's a king. You put it down. How many cards are in that deck now? It's not 52, it's 51. Now you're trying to find the probability of selecting a queen. Well, how many queens are still in the deck? Your first card was a king. How many queens are still in the deck? Well, how many queens are in the total deck of 52 cards? 4. And this reduces down to 0.078. Okay, so this is the probability of selecting a queen for your second card, but given the fact that the first card was a king. So it's a little bit more complicated with the probability rules here, but I hope we can get the hang of it. Now, think about this. Think about this one right here. I'm going to move myself up. Think about this problem. Find the probability that the child has a high IQ given that the child has the gene. So if you're on the notes, you can write down these numbers. So please write down those numbers. You have to fill out the table. But this is a high IQ, gene present, high IQ, gene not present, normal IQ, and so forth. So let's think about it, okay? Find the probability that a child has a high IQ, so has a high IQ, given that the child has the gene present. So high IQ, given that the gene is present, is 33. Okay, so I'm going to write this. Find the probability that it has a high IQ, given it has the gene. Okay, given that it has a gene. So what I'm first going to do is find the overlap, and that's what that's what that formula was, guys. That I wrote in the last slide. It really said this. So this is really just the probability of a high IQ. I'm just going to put H and the gene over the probability of getting the gene. Okay. So this formula right here is a formula I think is less intuitive than the other one, but this is actually works. This formula works a lot better. Why? Because this one right here, H and G, the high IQ and gene, that tells me that I need to find the overlap. So this right here, this numerator, that numerator says I need to find what we call the overlap. Okay? So what's the overlap of the high IQ and the gene present? Well, that's 33. So that is 33. And then what's the probability of just the gene? What's the probability of the gene present? Well, it's 72. So I look at the table, and that's 72 total with just the gene present, right? So then this is 33 all over 72, which reduces down to 0.458. And that's my probability. We're going to go through a lot more examples like this, so if that didn't quite make sense to you, that's okay. Just get it down. I'm going to erase, and then we're going to go through a couple more examples. I'm going to stick with this table. This table is the exact same table that I'm going to use, but now let's use it for different kinds of problems. Find the probability that the child does not have the gene. Now, what is that? Well, it's a complement. So find the probability of not having the gene. Okay? Well, of not having the gene not present is 30. Okay? So total number of people with the gene not present is 30. All over how many completely total? Well, it's 102. And it's just that simple, guys. And this reduces down to 0.294. So about 29%. Okay? Okay. Now, find the probability that the child does not have the gene given, now this is conditional, given that the child has a normal IQ. So I'm going to write down the huge long formula. So the probability of the child not having the gene given, vertical line, of a normal IQ, so N and then IQ. You know what? I'm just going to write normal. I don't want to confuse you. So normal IQ. Okay, what does this equal? Well, following my formula, I have the probability of given the gene, and I'm going to do the overlap here. The overlap, that's what I say, normal IQ all over the probability of just finding the normal IQ. Okay, so that is what my formula is. I'm going to cloud that. Let's find what it is. So this equals, what is this? Remember, guys, this is what we call, this numerator is what we call the overlap. Okay, so it's where on the table is there an overlap? Where on the table is there an overlap between not having the gene present and then the normal IQ? Where on the table does it give us not having the gene present and a normal IQ? So not having the gene present, normal IQ is that. So I'm going to write 11. And then over on, this is over the normal IQ. What is the total amount of people with a normal IQ? 50. So normal IQ, total amount of people is 50. And this reduces down to 0.22. So it's really not that complicated. It's just using your table to find your values, okay? But really the complicated part is just this formula because it kind of looks complicated. But go review back. It's not. Go back. Go back and see how I actually worded it when I was writing it down. Let's erase. All right, now let's get into independent events. What are independent events? Independent events are two events occur when one of the events does not affect the probability. One of the events does not affect the probability of the other events. So we can say two events, A and B, are independent when probability of B given A equals the probability of B, or when the probability A given B equals the probability of A. This is sort of complicated. I get that it's sort of complicated. We're not going to get too much into this though, because honestly, dependency and independency is actually very, very intuitive. We don't need to necessarily prove it with mathematics. It's just very intuitive, and I'll show you that soon. So events are not independent. That means that they're obviously dependent. Okay. This right here just kind of goes a little bit more deep into it. You don't need to write this down though, but to determine whether A and B are independent, you first calculate B, okay, and then calculate the givenness of B. If the values are equal, then the events are independent. If the values are not equal, then the events are dependent. Okay, so what I said was you calculate the probability B and then you calculate the givenness. Now the givenness is sort of interesting here. Remember this formula, if I expanded it out, is the probability of B and A all over the probability of A. Okay? So that's what that formula is. So this formula right here is the probability of B and A all over the probability A. So if this doesn't equal this, then that means it's dependent. The events are actually intertwined together. If they do equal each other, okay, then that means they are what we call independent. Okay, we're going to go through a couple examples. Determine whether or not it's independent or dependent. Selecting a king from a standard deck A, that's the first event, and not replacing it, and then selecting a queen from the deck as well. So I have the probability of queen given a king. Okay, so again, if I select a queen first, I put it down, not replacing it. That means there's 4, not replacing it. That means there's 4 kings still in the deck when there's 51 cards left over. Okay, but then I have the probability of a queen here is, 4 out of 52. Okay, so I know just looking at these, they're not equal. Okay, 4 out of 52 and 4 out of 51 are not equal, right? Because again, if I take a queen out, I look, okay, I put it back, or I don't put it back, I take a queen out of a 52 card deck, I put it down, there's 51 cards left in that deck. And then I ask, what is the probability of selecting a king, right? So that means there's 51 cards, but there's still 4 kings in that deck. Now, if I look at, okay, find the probability of just selecting a queen, well, selecting a queen is just 4 out of 52. That's what I started with, right? So that means they are dependent. Why are they dependent? They're dependent, guys, because the first event affects the other event. Selecting a queen affects selecting a king. Why? Because if I select a queen and I don't put it back, that means my total has changed. Since my total has changed, I no longer have the same event. If I no longer have the same probability here, then that means they're dependent. Okay? Let's erase this, and let's get to this one. Now, tossing a coin, getting a heads. Tossing a coin and getting a heads. A, that's the first event. And then rolling a 6-sided die, obtaining. So watch this. If I do a probability of 6, what's the probability of rolling a 6? Well, that's 1 out of 6. Now, what's the probability of rolling a 6 given that I toss a heads? Well, probability of rolling a 6 given that I toss a heads is still 1 out of 6. Okay, so this is what we call independence. Okay, this is what we call independent. Why are they independent? Because they're independent. Just think about it. Does tossing a head have anything to do with rolling a 6? Yes or no? No. I can toss a head and get a 6. I can get a 6 and then toss a head. I mean, they have no dependency. They don't affect each other at all. And since they don't affect each other at all, they're independent. What about driving 85 miles per hour and then getting in a car accident? Is that dependent or independent? You should all say that that is dependent. Okay? Yes, because if I drive really fast, the likelihood of me getting into a car accident is very high. What about smoking a pack of cigarettes per day and developing emphysema, chronic lung disease? Yes, that's of course dependent. Okay. And then exercising frequently and then having a 4-point grade point average. They may slightly be together, but honestly they're not. So that's what we call independence. Okay, so again, if they affect each other, if they're correlated together, they're dependents. If they don't affect each other at all, they're what we call independents. Okay? Now let's get to the multiplication rule. And then we're going to spend the rest of the time on the multiplication rule over and over and over and over again. The multiplication rule, what does it say and what does it mean? The multiplication rule of probability says this. The probability that two events, A and B, will occur in sequence is probability of A and probability of B equals probability of A times the probability of B given A. Okay, so that really what this means is dependency. Okay, this is what dependency is. I'm going to show you what that means in a little bit. So it can be dependent. So if an event is dependent, this is the formula I'm going to be using. If it's independent, I'm going to be using this formula, okay, where I'm just literally multiplying the probability of A times the probability of B. Now, why do I say in the slides this is and probability? I say it's and probability because it says and, okay, probability of A and B. That's what I'm saying. So this is the probability of A and B. That's why I say and probability. Okay? This simplified rule can be extended for any number of independent events, so it can be multiplied multiple times if you need to. So I'm going to go through an example after I go through these steps. I'm going to move myself right there. So what is it? So first, find the probability of the first event, and that's the number one thing. Find the probability of the first event. Number two, find the probability of the second event occurs, given that the first event has occurred. And then multiply these two probabilities together. This is for dependency. So these steps are for dependencies. So find the probability of the first event, find the probability of the second event, given if it is dependencies, okay, given that the first event has occurred, and then multiply the two probabilities together. Okay. First example, two cards are selected without replacing. So without replacing the first card. So if I don't replace the first card, does my total change in my deck? You should all say yes, which means this is what we call dependent. Okay, so I'm going to write that down. That's my first step. I know it's dependency. Okay, dependent. Okay, my second step is to find the probability of selecting a king and then selecting a queen. Okay, so the probability of selecting a king and a queen equals the probability of selecting a king times the probability of selecting a queen, given the fact that I already selected a king and I didn't replace it. So this is my formula for probability. Let's start solving this. What's the probability of a king? The probability of a king is just 4 out of 52. I have 4 kings, club, diamond, heart, spade, in the standard deck of 52 cards times. Now, if I draw a queen, if I draw a king first and don't replace it, then I'm going to be asking how many queens are in the deck. So if I draw a king, don't replace it. Okay, if I draw a king, selecting a king, and then selecting a queen. If I draw a king first, and then I go and select a queen, but I don't replace the king, what do I have? I have 4 queens, and then my new total is 51 because I didn't replace that king. Okay, so what does this equal? This actually equals 16 all over 2,652. Which of course is 0.006. Okay? Next one. Coin is tossed and a die is rolled. First off, I'm going to write that this is independent. Okay? The reason why it's independent is because a coin toss has nothing to do with the die being rolled. They have no structure to them at all. They have nothing tied to each other. Find the probability of getting ahead and then rolling a 6. So find the probability of selecting ahead and then rolling a 6. This equals the probability of getting ahead and then times the probability of a 6. What does this equal? Probability of tossing ahead is 1/2. Getting a 6 is 1/6. So this is 1/12, which then reduces down to 0.083. Okay, that is my probability. So not too bad, right? So this is dependent, what it will look like, and this is independent, what it will look like. Let's erase. Let's go on and go to this one, okay? To kind of get some more structure to it. Find the probability that the two salmon successfully swim through the dam. I love salmon, by the way. Okay, so, but the probability that the salmon swim successfully through the dam is 0.85. So we want to find the probability that two salmon successfully swim through the dam. So what is that? Well, first of all, it's independent. Why is it independent, Mr. Carlson? I'm glad you asked. It's independent because what one salmon does in the dam does not affect the other salmon unless they get into like a bar fight, all right? But the first salmon swimming through the dam does not affect the probability of the next salmon. They're two completely separate events. So since they're two completely separate events, they don't affect each other, it's independent. Now, two, I want to find the probability of two salmon. I'm just going to do SS. And so that means 0.85 and then times 0.85. This is also what we call 0.85 squared, and then this is 0.723. Okay, so really, I mean, you're starting to see probability is just honestly adding and multiplying stuff together. It's really just interpreting the problem. That's really what it is. It's just interpreting the problem. Okay, if you can interpret the problem correctly, you can answer it correctly. Okay. So let's go to the next one. Two cards are selected from a standard deck of 52 cards without replacement. So automatically when I see without replacement, that means I don't put it back. What does that mean? It means it's going to automatically be dependent because that means my total is going to change. Second step, find the probability that both of them are hearts. So probability that both are hearts equals, well, the first one is going to be 13 out of 52. There's 13 hearts in the standard deck of 52 cards. That's my first card being drawn. Multiply that by, now if they're both hearts, that means I took one heart and put it down. I didn't put it back. So that means, one, there's one less heart in the deck. Two, there's one less card in the overall deck, so it's going to be out of 51. Okay, so one less heart in the deck and one less card in the whole deck, so 12 out of 51. This reduces down to 0.059. Okay, sweet. All right, I'm going to erase this, and I'm going to continue doing just examples with the multiplication rule, okay? So an anterior cruciate ligament, okay, that's ACL, reconstructive surgery, the probability that the surgery is successful is 0.95. So what we want to do is find the probability that there's 3 successful surgeries, probability that none are successful, none of the 3 surgeries are successful, and then we also want to find the probability that at least one of the 3 ACL surgeries is successful. How do I do this? First of all, find the probability that 3 of them are successful. I'm going to write probability that 3 are successful equals. This is going to be 0.95 times 0.95 and then times 0.95. So this is 0.95 cubed, which equals 0.857. So it's about 86% that 3 successful surgeries occurring in a row will be, like I said, successful. Okay, will be good. That's actually pretty high. That's awesome. Find the probability that none of the 3 successful surgeries will occur. How do I do that? Well, first of all, I need to find the probability of not having a successful surgery. That's the first thing I need to do. Okay, well, that means I have to do the complement of having 1 successful surgery. This is 1 successful surgery, right? 0.95. So I need to do the complement of that, and that is 0.05. Now I can go and find the probability of having no successful 3 surgeries. So no successful 3 surgeries, and that is literally just 0.05 times 0.05 times 0.05, which equals 0.05 cubed, which then, of course, equals 0.0001. And this is what we call an unusual event. Why is it called unusual? Because it's less than 5%. Okay? It's less than 5%, that means it's unusual. All right? So since this is less than 5%, it is unusual. Okay? Find the probability that at least one of the 3 successful, one of the surgeries is successful. So how do I do that? Well, first of all, I need to kind of write some notation here. So the probability of x is greater than or equal to 1. So that's what at least means. 1 or more. That's what at least means, right? 1 or more. Probability that at least 1 or more of the 3 surgeries are successful is equal to 1 minus the probability that none, okay, are successful. That none are successful. But I just found that none of the 3 are successful, right? I found that in my second example. So this is the first step. The second step is to do this. So I do 1 minus, is 1 minus, and then this is 0.001. Okay, so why do I have to do this? Because at least one of the 3 ACL surgeries is successful. What that means is it's 1 or above. So I need to do the complement of 1. I need to do the complement of none of the 3 successful surgeries, because this is none of them, and I at least want 1. So that means I do 1 minus the none of the successful surgeries. What does this equal? This equals 0.9999. What does this mean? This means, what's the probability that out of 3 surgeries that at least one of them will be successful? It is literally 99.99% chance. Okay? So you can bet your dollar on the fact that you will have at least one of those surgeries be successful. And that's good news, right? That's good news. All right. Let's erase. Let's go for more probabilities. Okay. Try to do this one yourself, to be honest. You can try to do this one yourself because it's very, very similar. Probability that a particular rotator cuff surgery is successful is 0.9. So find the probability that 3 rotator cuff surgeries are successful. So what this is the probability that 3 are successful is just 0.9 cubed, which is 0.729. If you got that, then you're awesome. Find the probability that none of the 3 rotator cuff surgeries are successful. How do I do that? Well, first step, I need to find the probability of the complement. So none are successful, which is 1 minus 0.9. Because this is telling me that there is one. That's the probability of at least one being. This is the probability of one being successful. This is the probability that none are successful, which of course is 10% or 0.10. And then this right here, the second step is then I'm going to include the probability that none of the 3 are successful. So that means this is going to be 0.10 and then cubed, which is 0.001. Okay, and then that at least one is successful in those 3. So I do the probability of x has to be greater than or equal to 1, and this has to be 1 minus what I just found. And so this equals 0.999. Okay, sweet. All right, I'm going to skip example 5 and example 6, and those are the next examples. You can look at the key for that, but I'm going to skip those because those are a little bit more like advanced. So Feel free to kind of look at those examples on the key, but I'm not going to go through them. What did we learn? We learned how to find the probability of an event given that another event has occurred. We learned to distinguish between independent and dependent events. We have learned how to use the multiplication rule to find probability of two events occurring in a sequence, and also to find conditional probabilities. So that is what we did. Make sure you do your notes tonight. Finish them. You have a homework quiz over 3.2 tomorrow. So please go through your homework. If you have any questions, please email me as much as possible. I will answer them. Or you can come on the Google Meets link and we can discuss whatever you're struggling with. But it's been Real Stats. I hope to catch you in the next video. Peace out.